Alrighty, good morning, A1 Algebra 2 CP. Happy Thursday morning. Couple people just popping in, which is fantastic. Julia, good morning. Everybody's here, good morning. Today, what I'd like to do with you is Brock, B-Rock coming online. Excellent, fantastic. I was worried for a little bit. Good morning. What I'd like to do today is I would just like to show you more examples of graphing rational functions that contain holes in the graph. Remember from last class, I think these are the notes here, we talked about the fact that if you graph one of these rational functions and after doing some factoring, you find a matching factor that cancels out in both the numerator and the denominator, it's great because it helps us simplify the graph a lot. I'd much rather graph something like this than try to graph something like this way up here. But it doesn't come for free. It comes with a cost. And the cost is the fact that it has a singular undefined point that we have to indicate, that we first have to identify and then have to indicate in the graph. So again, what we're looking at now is just building on our previous idea of rational functions. Now talking about rational functions that you need to do a little bit of factoring, a little bit of canceling first. That's what creates these things called holes in the graph. And once you have that, you can then go ahead and just graph normally, indicating the hole at the very end. So that's really the only twist here. I just want to spend one more day with you talking about more examples on that. Just a couple reminders before we get started, as per usual. Everybody's gotten used to the fact that their microphones are muted and their webcams are turned off, which I really appreciate everyone's cooperation. Hopefully everybody also got used to filling out the attendance form on Google Classroom. If you just so happen to forget, make sure you do that now. Very important, especially it's very important, especially considering that this is our first period class, so it does count for your daily attendance. So make sure you fill out that attendance form on Classroom. Let's see. Is there anything else I need to remind you? Yes. One more thing. We do have a progress assessment coming your way after this class. It will be sent via email, just like the others. It will be due by Sunday night at midnight, so that gives you all of today, the rest of the afternoon, plus tomorrow all day, Saturday all day, and Sunday all day to submit that progress assessment to me. Again, just like last week, the reason for the Sunday deadline is so that I can grade it on Monday and get it back to you. I know I was a little slow putting the grades in this week, but just a lot of stuff came up, so hopefully next week will be a little smoother on that front. What else did I want to tell you? But yeah, just like last time, make sure you submit it via email. You can take pictures of your work, attach them, and send them back. That's been going very well for my math classes all across the board, so I think I don't see any reason to not continue with that trend of submitting your work via email. The other thing I want to say is just to make sure that you are completing the work on time. It's very important, especially since I want to provide feedback to everybody at a timely manner. I understand that things come up and things are unexpected, and this period of distance learning is unpredictable for a lot of reasons. But that being said, if you have the opportunity to submit it in a timely way, please do that. And I know the majority of you have certainly done that, but I believe there were like 6-ish assessments that came in after the deadline, which is what ultimately halted me from being able to post the answers and provide feedback a little sooner than I would have liked to. Or rather a little sooner, rather than delaying like I had to kind of do. So just a little FYI, please make sure you get that on time, just because it kind of halts the whole process for being able to provide feedback to everybody. All right, but if you do need help, that being said, if you need help or have questions, please feel free to reach out to me. You can send me an email at any time. It just goes to my phone, so I can usually respond right away. It's not like I'm going anywhere. So please make sure to reach out to me. I'll respond very soon. If you want to meet anytime on the Friday, tomorrow, to go over some problems, I'm happy to do that with you as well. All right, so just send me a message. Say, hey, Miss Giorgio, can we meet? Can we set something up? No problem. All right, that being said, let's go ahead and dive into some rational functions that require some factoring before we solve them. Let's do it. Starting with this one. I have 5 of them prepared for you today. I don't know if I'll get through all 5, but I'll try to do as many as I can. Start with this function. We got 3x squared plus 21x plus 36, all divided by x squared plus 6x plus 8. And I want to go ahead and sketch a graph of that rational function. Well, hopefully you can kind of think to yourself, that looks crazy. That's difficult. It's annoying. It's confusing. It's got all these terms everywhere. Let's see if we can factor and simplify before diving right in. One thing that I do want to emphasize is, yes, you could do that without simplifying, but like, how would you find out what value for x if you plug it into the denominator is equal to 0? That would just be a very difficult question to answer without factoring. Before we actually factor, though, hopefully you can notice in the numerator, we can take out a little bit of a GCF, right? In the numerator, before we actually break down those trinomials, let's take out that GCF of 3, because that will actually help my factoring step a lot. Because now I only have to worry about leading coefficient 1 with the x squared term. Just like that, right? Now I can go ahead and break those terms down. So we could say in the numerator we're going to break down to 2 binomials. In the denominator we're going to break down to 2 binomials through factoring. Factoring the numerator, let's see, I need x times x to multiply to x squared. Everything's positive, so let's keep everything positive. And lastly, we're looking for factors of 12 that can combine to 7. I think that's just 4 and 3. 4 plus 3 is 7. We move in the denominator, same deal, where we have x and x, same deal, where everything's positive. And lastly, we look for factors of 8 that can combine when you distribute to get 6. That's going to be 4 and 2. 4 times 2 is 8, and 4 plus 2 is 6. Now looking at those expressions, hopefully you notice, ooh, x plus 4 over x plus 4, that's going to cancel out. And that gets us down now to 3 times x plus 3 all over x plus 2, which is a graph that we can go ahead and tackle, right? Remember, though, that this cancellation does not come for free. That cancellation of a factor of x plus 4 means that we now have a whole at x equals negative 4, right? Because negative 4 plus 4 would have been a problematic thing in our original version of the function. Right, negative 4 plus 4. So that's not a problem anymore with the simplified version, but it does create this hole in the graph. So just keep that in mind. Now I can go ahead and test some points, and then I can sketch a graph. So let's test some points first. We got to find the asymptotes first. Let's find our vertical asymptote is negative 2, because negative 2 plus 2 would be dividing by 0, which is bad. Our end behavior asymptote, compare the degree of the numerator and the denominator. The degree of the numerator is 1. The degree of the denominator is also 1. Since they have the same degree, we're going to create a fraction out of the leading coefficients and then tack on the vertical shift. There is no vertical shift here, so we don't actually have to worry about that step. But your leading coefficients here are 3, because this would be 3x, and 1. So 3 divided by 1 would make that end behavior asymptote of y equals 3. Okay. Does anyone have a question as to why the end behavior asymptote would be y equals 3? Or even why the vertical asymptote is negative 2? And as you're thinking about that, I'm going to go ahead and sketch in the graph here. Okay. We got our graphs. Kind of looks like this. Here's our end behavior asymptote at 3. Here's our vertical asymptote at negative 2. Just like that. All right, no questions, it doesn't look like. So now what I can do is I can go ahead and just test points like I'm used to doing. I'll do it over here. Okay. Just like before, I want to plug in 2 x coordinates to the left and 2 x coordinates to the right of the vertical asymptote. Here my vertical asymptote is negative 2, so I'm going to plug in negative 4, negative 3, negative 1, and 0. Okay. So what we can do is we can just take these values and plug them into the simplified version to find out what we're going to get. What I would do is I'd take negative 4 and plug it in. In the numerator, we get negative 4 plus 3, which is negative 1. 3 times negative 1 is negative 3. Over negative 4 plus 2 is negative 2. So negative 3 divided by negative 2 is positive 1.5. Before I draw that point in, actually, do you notice the fact that we also have a hole at x equals negative 4? Kind of a peculiar thing that happens in this problem, the fact that we have a hole at this point, and it actually just so happens to be one of the values we plug in. That's okay, though. What we're just going to do is we're going to represent that point just with an open circle to account for the fact that there is a hole and not a single point at negative 4, 1.5, because we identified that there's a hole at negative 4. What you can do instead of going in that order of operations, what you can do instead is just graph it normally with a closed circle graph the rest of the points normally, all with closed circles, draw your curve, and if you're working in pencil, you can then go back and erase and draw an open circle. A lot of students prefer to do that, so they're just like, they don't have to worry about the hole until the very, very end, where they're just like, oh, I'm just going to graph normally, and then at the very end, I'll make my adjustment by erasing this little mark and putting an open circle. That's absolutely fine as well. And that, by the way, is why I make this little note over here that we have a hole at x equals -4, because otherwise I'd probably forget. Like if I didn't write that little arrow with the note, I'd probably not remember to go back and plug in and account for that hole. All right, so just a little FYI. -3 then goes in. Going back to our plugins, in the numerator, I get -3 plus 3, which is 0, and 3 times 0 is 0. In the denominator, -3 plus 2 is -1, so I get 0 divided by -1, which is 0. Point right there. That's now just a regular old closed circle. -1 goes in. In the numerator, -1 plus 3 is 2. 3 times 2 is 6. In the denominator, -1 plus 2 is 1. So I get 6 divided by 1, which is 6. So that is 1, 2, 3, 4, 5, 6 right there. 0 goes in the numerator. 0 plus 3 is 3. 3 times 3 is 9. Divided by 0 plus 2, which is 2. 9 divided by 2 is 4.5. 4.5, which is right here. 1, 2, 3, 4.5. Okay. Hopefully you notice the symmetry between everything that's going on. And now I can go ahead and just draw my curves, which will be approaching but not touching the asymptotes. Approaching but not touching the asymptotes. And we have our singular undefined point already accounted for in the graph. Again, to emphasize, if you wanted to say just draw a regular old closed circle, definitely works better if you're working with pencil, and then erase it after the fact to put an open circle there, that's absolutely fine as well. All right, but that should be a problem that you would be able to graph and deal with and handle on any sort of assessment. Okay, maybe even the assessment coming your way pretty soon. I'm just going to separate this space over here. Any question, comment, or concern about that? Just to reiterate, you would not be responsible for doing the domain and range on any of these problems that have holes in them. You certainly can do it, but you wouldn't be asked to do that on an assessment. Certainly something you're capable of. We're good on that? Alrighty, let's try another one then. I take your silence as yes, Mr. Giorgio. Sounds great. You're doing a wonderful job. We got 4x all divided by x squared minus 3x. I like this problem. And then plus 1 on the outside. Okay? Hopefully, again, that indicator of x squared is a prime time. It actually is an indicator that we need to factor, right? If you look at x squared, you should be like, ooh, whenever I see x squared, that usually means factoring. That's what we have to do down here as well. Here, it's not a traditional trinomial, but we could certainly take out a greatest common factor, a GCF of x. Rewriting this as 4x times x, or over x times x minus 3 plus 1. See that? How we pull out a common factor of x from here and here? Just like that. Now, what we can do is, because we have this common factor of x out here and this common factor of x up there, we can cancel out those x's, reducing this down now to 4 over x minus 3 plus 1. But of course, just like before, that does not come for free. It does come with a cost. And the cost of that is there is now going to be a hole at where? We just crossed out a regular old x. Here, when we saw x plus 4, we saw it created the hole at -4. Here, when we're just crossing out x, it creates the hole at x equals 0. Because what value for x would cause dividing by 0? It would be 0 itself. Because plugging in 0, you'd get 0 times whatever this is 0 in the denominator, right? A lot of students have a common misconception. They say, oh, when it's just an x that crosses out, that creates a hole at x equals 1. For whatever reason, they jump to that. But the factor that would create a hole at x equals 1 would be x minus 1, right? It's not just regular old x. When it's just a regular old x, it's a hole at x equals 0. Okay? So let's keep that in mind. Now we're going to go forward from there. This graph is definitely something we can handle at this point. Identify the vertical asymptote, which is x equals 3. The end behavior asymptote, which degree of denominator is larger, so it's 0 plus the 1, y equals 1. Again, I'm going to go through this a little faster now because this is something that, like, especially down to this point, you should be very comfortable doing that. I'm going to go ahead and draw my graph. I'll do it over here in this corner. we have, let's see, vertical asymptote at 3, end behavior asymptote at 1 right there, vertical asymptote right there. Excellent. I can go ahead and create a chart now to test some points. We're doing 2 to the left and 2 to the right of that vertical asymptote. So I'm going to do 1, 2, 4, and 5. That's 2 to the left, 2 to the right of the vertical asymptote. Let's take these values, plug them in, and see what we get. If 1 goes in, I get 1 minus 3 is negative 2. 4 divided by negative 2 is negative 2. Plus 1 is negative 1. So I got a point at 1 comma negative 1 right here. 2 goes in our expression here. 2 minus 3 is negative 1. 4 divided by negative 1 is negative 4. Plus 1 is negative 3. Got another point right there. Next, 4 goes in. 4 minus 3 is 1. 4 divided by 1 is 4. Plus 1 is 5. So that's 4 comma 1, 2, 3, 4, 5. And last but most certainly not least, 5 goes in. 5 minus 3 is 2. 4 divided by 2 is 2. Plus 1 is 3. 5 comma 3. 1, 2, 3 right there. Okay? Now I'm going to draw my curves approaching but not touching the asymptotes like that. One thing I have to remember, though, is wherever we cross this threshold of x equals 0, which is the y-axis, that's where we have our hole. So I'm going to draw my curve as normal, approaching but not touching. But wherever now I'm going to cross that threshold of the y-axis, I'm going to draw my open circle. Okay? Again, it doesn't mean that it's on the x-axis specifically. It doesn't mean that your curve has to go up to meet it. It's just in the natural drawing of your curve wherever it would cross this barrier. That's the best way I think I can explain it. And that's now a graph of that. Questions, comments, concerns about that? Feeling happy? Feeling good? Well, then let's do some more. Let's do some more. Why stop there, right? Let's go with this. I like this one. How about f of x is equal to, let's sketch a graph of 3x squared plus 6x, all divided by x squared minus 4, and then minus 1. Ooh, good old difference of two squares coming back in the denominator. Fantastic. Don't want to forget about your good old difference of squares. It's going to come back when you least expect it. So in the numerator, we can definitely do some factoring here where we have to do a GCF. The greatest common factor in the numerator, I see 3x. That leaves us with x plus 2. Once we pull out 3x from the first term, there's x left. Once we pull out 3x from the second term, there's just a factor of 2 remaining. All over. How do we factor something like x squared minus 4, a little difference of two squares? It's going to be x, and x is the square root of x squared, and then 1 positive, 1 negative, plus 2, and minus 2. Okay, and then minus 1 on the outside. Right? You should remember that a difference of two squares, x squared minus 4, the way you would factor that down is you just take pretty much the square root of both of these. We get the square root of x squared is x and x, the square root of 4, 2 and 2, and 1 plus, 1 minus. Okay? Think of, just a little refresher, if you were to go back and factor something like x squared minus 25, that would be x plus 5, x minus 5. X squared minus 49, x plus 7, x minus 7. X squared minus 100, x plus 10, x minus 10. Alrighty? So, now that we have that, we can see this factor canceling out here. Again, not for free though, creates a hole at x equals negative 2. That leaves us now with 3x divided by x minus 2, and then minus an additional 1. Does everybody see that? Now we can go ahead and find our asymptote, test points. So our vertical asymptote here would be 2, because 2 minus 2 would result in dividing by 0. Our end behavior asymptote, both the numerator and denominator have the same degree. It's x to the first power, x to the first power. So what we're going to do is create a fraction out of these coefficients and then tack on the vertical shift. 3 divided by 1 is 3, minus 1 is 2. So our end behavior asymptote is also 2. Okay. Questions on that? Feeling A-okay. All right, let's draw in our thing here. I got my axes. my vertical asymptote at x equals 2, my end behavior asymptote at y equals 2. Now we can go ahead and test points. Just like before, we're picking 2 points on the left and 2 points to the right of the vertical asymptote. Hopefully, if I say it enough times, it'll sink in. 2 points to the left, 2 points to the right. Vertical asymptote's at 2. We're going to pick 0, 1, and 3, and 4. Take these, plug them in. When we plug in 0, we're going to get in the numerator 3 times 0 is 0. Divided by 0 minus 2 is negative 2 minus 1. So I get 0 divided by negative 2 is 0, minus 1 is negative 1. 1 goes in. In the numerator, 3 times 1 is 3. In the denominator, 1 minus 2, negative 1. Minus an additional 1. 3 divided by negative 1 is negative 3. Minus 1 is negative 4. Let's go ahead and plot those points. We got 0, negative 1 right here. We have 1, comma, negative 1, 2, 3, 4 right there. 3 goes in now. In the numerator, 3 times 3 is 9. In the denominator, 3 minus 2 is 1, and then minus 1. 9 divided by 1 is 9, minus 1 is 8. So I got 3, comma, 8. That's 1, 2, 3, 4, 5, 6, 7, 8, way up there. Okay. And last but not least, 4 goes in. In the numerator, 3 times 4 is 12. In the denominator, 4 minus 2 is 2, and then minus an additional 1. 12 divided by 2 is 6, minus 1 is 5. So I got my last point at 4, comma, 1, 2, 3, 4, 5. Anybody have a question as to how I got those points? We're just taking and plugging them in. Remember that after you factor and simplify, you can and should plug in these values into the simplified version. There's really no need to go back to our original version. You can and you'll get the same answers, but it's just overly complicated. You might as well just use our simplified version of the function. The last thing I need to account for is the fact that we have this hole at x equals negative 2. So I'm going to draw my graph. Curves approaching but not touching the asymptote. Approaching but not touching the asymptote. And just in the natural progression of drawing my curve, it looks like it crosses negative 2 right there. I'm going to indicate that with an open circle. Okay? See how it crosses that boundary of where x would equal negative 2? Right there. There, maybe it's a little clearer. Right there. Right? That's where x would equal negative 2. So wherever your curve happens to cross that threshold, you're just going to indicate with an open circle and continue about your day. Alrighty, no questions. We're feeling good. We're feeling comfortable and confident. I mean, that's great news. But if you do have a question, don't be afraid to ask. Give you some time to soak it in. Feeling comfortable and confident? All right, all right, all right, all right. One more to go then. One more to go. I like this one a lot. I mean, I like them all. Let's not kid ourselves. I like all math. We got 3x squared minus 48, all divided by x squared plus 3x minus 4. I like this problem a lot because there's a lot of factoring that actually occurs here. Ready? What I'm going to do is I'm going to factor down the numerator a little bit first. Could take out a greatest common factor of 3. If I do that, we're left with x squared minus 16 because 3 times 48 would be 16. Or no, other way around, jeepers. 3 times 16 would be 48. That was embarrassing. 48 divided by 3 is 16. In the denominator, I'll leave that alone for right now. Now, hopefully you're thinking to yourself, ooh, whoa, how cool is that? Just waving your arms around like this. You're like, wow, x squared minus 16, that's just a difference of 2 squares. I threw my pen. I got so excited. That's a difference of 2 squares. We can factor that down now to be x plus 4 and x minus 4. In the denominator now, I'll factor that trinomial down to be, let's see, x plus 4 and x minus 1. Hopefully everybody can see that, right? We need x and x to get x squared. 1 negative, 1 positive, because we're multiplying to a negative. We need different signs. And we need positive 4 and negative 1 to get my positive 3 in the middle. Now, x plus 4 divided by x plus 4 goes away. That creates a hole at x equals negative 4, because negative 4 plus 4 would have caused division by 0. I'm left now with 3 times x minus 4 in the numerator. In the denominator, I'm left with x minus 1. And now we can go ahead and find the information and graph normally. Ready? I'll run through this part really quick as we approach the end of class. We got our vertical asymptote is x equals 1. Our end behavior asymptote, there's no vertical shift, so it looks like it's just leading coefficient of 3 divided by leading coefficient of 1, so it would be y equals 3. Notice I would do that because these have the same degree, degree 1, degree 1. Then I can go ahead and sketch my graph and test some points. Let's do that now. Sketch my graph. We got our vertical asymptote at 1. Our end behavior asymptote at 3. Okay, let's test some points. I'll draw my little chart down here. Everybody can see that still on the screen, right? Yeah. So if my vertical asymptote is positioned at x equals 1, I'm going to go ahead and plug in 2 to the left, 2 to the right. We got -1 and 0 on the left. We have +2 and +3 on the right. Let's take these values, plug them into the function, and see what we get. -1 goes in. -1 minus 4 is -5. 3 times -5 is -15. Holy cow. Divided by -1 minus 1 is -2. -15 divided by -2 is positive 7.5. So we got a value at -1, comma, oh, that's right here, comma 7.5. 1, 2, 3, 4, 5, 6, 7 and a half. Oh, jeepers. I hope this fits on the graph. It's a big, tall one. 0 goes in. 0 minus 4 is -4. 3 times -4 is -12. Divided by 0 minus 1 is -1. That's positive 12. Oh, geez. Oh, boy. 1, 2, 3, 4, 5, 6, 7, 8. I lost count. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're going to bleed into the other problem here. We're bleeding into the other problem. I'm going to draw my curve, approaching but not touching the asymptotes. On 2 now. I hope we have enough room down here. 2 goes in. 2 minus 4 is -2. Divided by, oh, sorry, times 3. 2 minus 4 is -2 times 3 is -6. In the denominator, 2 minus 1 is 1. So I get -6 divided by 1 is -6. That's not that bad. We can do that. 1, 2, 3, 4, 5, 6. And lastly, 3 goes in. In the numerator, 3 minus 4 is -1. -1 times 3 is -3. Divided by, in the denominator, 3 minus 1 is 2. Oh, that's a nice easy one. -3 divided by 2, -1.5. So that's going to be right about here. Okay. These points are very far away from those asymptotes, or especially the end behavior asymptote. But by having the end behavior asymptote there, it shows you a guideline of how your curve should behave. They need to approach but not touch that asymptote. And keep in mind, we do have the hole at x equals -4. So first I'm going to start approaching but not touching the asymptotes like this. It's not bad. Approaching, we have to go way up for that one, but not touching the asymptotes. And wherever my curve happens to cross the threshold of -4, that's where I'm going to indicate the hole. Let's see. This is -1, -2, -3, -4. So wherever we cross -4, I'm going to go ahead and indicate that that's an open circle. Okay, just like that. There we go. Look at that. We were able. We fit it. We did it. That wasn't bad. Took a little bit of work to extend our graph, but we made it. We made it happen. We made it happen. Any questions, comments, concerns about that at all? Okay, that's definitely on the harder end, probably the most difficult problem that you could expect to see in a section like this, where you'd have to not only factor using a little GCF on the top, but then also a difference of squares, and you get some numbers that create this pretty large graph. I don't know if you'd be faced with a problem like that on an assessment, but definitely it would be the hardest that this sort of gets, if that's comforting to hear at all. All right, so I know we're just about out of time. Again, I want to remind you to make sure you complete that progress assessment. The other thing I want to just throw a quick reminder out there is that these lessons are recorded and they are available to be watched back. They're published on YouTube, so please make sure you check them out if you need a refresher. They're there. All these examples are available for you. They're all done out step by step, as you can see if you just rewatch. So please go ahead and do that. They're all linked on Classroom. The playlist is linked. So if you ever need to go back and have a refresher of this idea, or maybe just see some examples done out again, please go back. I think it's an excellent resource for you to use. Okay. Next time, my Google thing just dinged. Next time, we are going to go ahead and talk about equations. All right, so we're actually done with graphs, besides your progress assessment, which should have gone out via email just now. We are done with graphs for the year in Algebra 2 CP, actually, so you can be like, woo, this is the last graphing thing that we do. Little bittersweet though, because that of course means that we're going to shift gears to more algebra. We're going to be doing some solving equations involving expressions like these that have x's in both the numerator and denominator. All right, so next time we're going to start with a brand new topic on solving rational equations. In the meantime, please make sure you get the progress assessment done and submitted to me by Sunday night. I'll grade that and have that to you on Monday, and then we'll work into some solving equations. I think that sounds like a great plan to me. Hopefully it sounds like a great plan to you as well. Regardless, I hope you stay safe, stay healthy, and have a fantastic rest of your day and weekend. Thank you for your attention and focus and for staying a couple minutes after. I'll see you guys next time. See you later. Have a great day. Thank you so much for being respectful. Appreciate that. Yes, Ben, you do. You do have to check in for attendance tomorrow morning. I should have mentioned that while everybody was here. Drat. I'll send out an email to remind everybody. Yes, you don't have to come to the meet. You just have to fill out the form. I'll send an email to remind everybody. Just have to fill out the form for attendance. Okay. Have a good day.